between the 3.35 volt regulator IC used in Lenovo Y570 and the TPS 51120, that is the regulator IC used in DV2000. What are the differences and why are those differences? Okay, always one should ask questions, why are those differences? So here this LDO, the LDO generated by 5v_al, and when LDO is generated, when it gets enable LDO, and enable LDO is generated by the resistance divider. You see in the previous slide, enable LDO, when enable LDO is generated, when this supply, this V in through resistance divider goes to the enable LDO, when it gets enable LDO, it outputs LDO, that is labeled as 5v_al, and this 5v_al is very important because generates VCC, PVCC and the 3.35 volt enable signal. Okay, when it gets enable signal, then the regulator, the RT8206M, the regulator, it will generate signal U gate and L gate, and this, as we have already discussed in the basic electronics, this MOSFETs basically are type of switches, and once this closes, this opens, this closes, this opens, and it switches to generate a voltage, a lower voltages, and this is a regulator which generates lower voltages is called buck regulators, and this is a buck regulators. It is generating a lesser voltages from V in, and V in is approximately 19 volt, and we are trying to generate a 3.3 and 5 volt from 19 volt through switching of this MOSFET, and switching of these MOSFETs is controlled by the gate, and this signal U gate to and L gate to, this controls the switching on and switching off of this MOSFETs, and when they will generate this signal, when it will get enable signal, and the enable signal in RT8206M comes from LDO, and LDO will get generated when V in through resistance divider goes to the enable LDO pin. Okay, till now we are clear? The steps should be very clear, because if steps should be clear, then we can trace in a step by step, right? If we miss any step, then we'll overlook it, and once you have a tendency to overlook anything, it's become very hard to repair. We must not overlook anything. Maybe it may be complex, but if you break it in smaller parts, we can understand it very smoothly. Okay, so what we have studied till now, the V in is going to the IC, V in through a resistance divider is going to the enable LDO pin, it generates LDO which is labeled as 5v_al, that 5v_al powers VCC and PVCC. VCC is for supplying the internal logic of 3.35 volt regulator IC, where the PVCC is supplied to the gate drive circuit, internal gate drive circuit, which will generate this gate drive for the lower MOSFET. Okay, and this 5v_al is also generating the enable signal. So we must check the enable signal. If we are not getting this enable signal, maybe this 5v_al is not connected, or maybe this resistance may be short, or maybe this resistance may be open. Okay, so we have to check everything. It gets enable voltages, then this the regulator IC will generate DH, DL, drive high, drive low. Okay, and drive high means turn this switch on, drive low means turn this switch on. So we have off, on, off, on. Okay, and it will switch to generate 3B CPU. We'll go into the greater detail how does a PWM regulators work, but right now let's check the steps. Similarly, over here the V in is going to the top MOSFET. Okay, this is again a N channel MOSFET, the arrow is inside, current flows from drain to source only when VGS is positive. Okay, so here the 5V underscore L is there at the enable pin, and 3.3 enable, that is going to the enable 1. So enable 1, so it will generate the signal U get 1, you see, and the L get 1. Okay, L get 1. So again this will turn off and turn on to generate plus 5V CPU. So this is the step of generating, but there are certain pins like phase 1, ILIM1, FB1, BYP. What are the meanings of this pin? Why those pins are? Okay, so we'll understand these pins also, why this is out one, and why any regulator have a structure like this. We'll cover this in this class. Okay, so till now we are clear with the steps. Let's again see these steps over here. VIN is coming, okay, VIN is coming over here at the pin number 6. Then this VIN is divided through resistance divided going to the enable LDO. It gets enable LDO generator marked by 5V underscore L. It goes to the VCC and PVCC and also goes to the enable pin, and then this regulator will generate drive high, drive low signal to turn off this MOSFET to generate a lesser voltages from a high voltage. This is an example of buck regulators. Now we'll understand all the pin details. We'll go into the data sheet, and before going to the data sheet, let's consider a case of universal regulator. How does a regulator operate, and that too a pulse width modulation regulator. Okay. Okay, so we have covered the working of 3.35 volt regulator IC till now, and we have seen how does it work in Lenovo Y570, but we must know the working of each of the pins of this 3.35 volt regulator IC, as it is one of the most important power regulator present on the notebook motherboard. But to understand the working of each of the points of these regulators, we have to understand how does a DC regulator works and what are the type of DC regulator. Basically this class would be a little theoretical, but it would quench the thirst of some of the electronic engineer who are doing this course of laptop repair to understand electronics in a better way. And to them who are just have joined this course for repairing laptop motherboards, I'd also say to listen to this my class. And this is, I have tried to simplify this class as much as I can, but this if you want to study entire things about DC regulator, you must have a degree of I think a graduate degree in electronics to understand certain things, and I have skipped those things purposefully because those are not required when we are trying to diagnose any chip and we are going to know the working of that chip. We don't require those mathematics, so I have skipped those mathematics. And if somebody is really interested to have knowledge about those things also, then he can personally message me and I can discuss those things with him. So let's go about to discuss the DC regulators. Why do we need DC regulators? The question is, why actually we need DC regulators? We need DC regulators because if we talk of a notebook motherboard, we can see at every point there is certain fixed voltages present, and all those voltages are coming from a adapter in V-in that we have already discussed. Those all voltages will come out from that V-in, so there must be some mechanism to convert a high voltage into a less voltage. And on a notebook motherboard, the source is adapter and battery, and the sink is processor. Processor requires power to execute instructions, And similarly, the south breeze and IO controller, they also require power to execute instructions, to execute the work. So we need DC regulators to generate different kind of voltages from a common V in or DC bat out. Now the question is, there are two kinds of DC regulator. We have seen while discussing the 3.35 volt regulator in the Lenovo Y570 that there is an LDO. LDO is low drop out, and that is a linear regulator. And we have seen the generation of 3 and 5 volt through switching on and switching off of MOSFETs, and that is, we call it pulse width modulation regulator. So why those two types of regulator? Why one linear regulator and why one pulse width modulator regulators, and what is the difference between them? In linear regulators, we generate lesser voltages through resistive element, right? Resistive element, like we have a 12 volt, and if we put a resistor across it, there will be some drop of energy, there will be some energy consumed across that resistor that will help drop the voltages. That is one way, that is very simple way, that is, we call it low drop out regulators. But another is the PWM, that is pulse width modulation. We can generate a lesser voltages from a higher voltage, or we can generate a higher voltage from a lesser voltage if we control the turn on and turn off of switch. And let's see the next slide. So the power switch, the switch, as we discussed in the Lenovo Y570, the switch was upper side MOSFET and the lower side MOSFET. Those are switch. So the switch is critical to pulse width modulation regulators, and by controlling the turning on and turning off of this switch, we can generate different kinds of voltages from a common voltage. And so what are the key elements in a PWM regulators? One is two switch, one inductor, one capacitor, and one feedback. That is present in every PWM regulators. What is the main function of inductor? What does the inductor do that differentiate between a linear regulator and a pulse width modulation regulator? In a pulse width modulation regulator, inductor basically limit the slew rate, the rate of increasing current or rate of decreasing current, that is slew rate. So the inductor, basically inductor is such an electronic device, such an electronic component that it has inertia. It has an inertia inside it. It doesn't allow the current to go down instantaneously. Similarly, it doesn't allow the current to rise up instantaneously. It has a inertia, right? It has an inertia. So this inductor is the key difference that differentiates between a PWM and a linear regulator. The inductor limit the slew rate, and in a linear regulator we have a much higher energy loss because there is a resistive element. There is a resistive element across a linear regulator, and in a resistive element we have loss of power. Power is directly proportional to I square R. I square R. So the R is resistance, and if there is a voltage drop, then the power loss will be too much. Whereas in inductor, the power loss is less. The power loss is less, and we'll discuss how this is less, because an inductor stores energy, right? It stores energy, so the power loss is less. So to differentiate between a linear regulator and a PWM regulator, what are the basic differences? The basic difference is, in a linear regulator we generate a less voltage through a resistive element. We try to drop the voltage across a resistor, whereas in a PWM regulator we try to generate a lesser voltages. I'm talking about buck regulator. Buck regulators are type of regulator which generate lesser voltages, because in a notebook motherboard we generally have a buck regulators, because we are trying to get a lesser voltages from a high voltage. So in a PWM regulator we have two switch, one inductor, and one feedback. That is PWM regulators. But if we go into studying this the data sheet of the 3.35 volt regulator IC, the different types of regulator IC, we'll see that there are various modes of working. One is voltage control, another is current control. What those steps are, if we do not understand those steps, that will seem something like confusing, and if there is any confusion, that would provide an hindrance to diagnostic. So you must clear at least all the important concepts, and that's why this is my class, to understand the 3.3 5 volt regulator IC, all pins. Okay, so let's go to the next slide. And as I said, the switching regulators, there are different types of switching regulators. One is the buck converters, another is boost, and another is inverter. And we'll see in the next slide what are those different types of regulators. And as I have spoken, a switching regulator uses a power switch, an inductor, and a diode to transfer energy. And we'll see in some switching regulators we don't have two MOSFETs, we have one diode and one inductor. What is synchronous switching regulator? What is asynchronous switching regulators? And those are the differences. The synchronous switching regulators are those kind of switching regulator which employ two MOSFETs, whereas asynchronous switching regulators are those which doesn't employ MOSFET, each employs one diode. And that is the difference between asynchronous and synchronous. And synchronous rectifiers, they are much efficient because they use MOSFETs, and in a MOSFETs we have lesser energy consumption. Okay, so I think I'm pretty much clear with what I'm speaking till now. I'm telling that a linear regulator generates a less voltage through a voltage through the loss across a resistors, whereas a switching regulator generates lesser voltages by controlling the turning on and turning off of two switches. And there are two kinds of switching regulators, one is synchronous and another is asynchronous. In a synchronous switching regulators we have two MOSFETs as acting as a switch, whereas in asynchronous switching regulators we have one diode instead of MOSFETs, and we'll see what are the differences between both of them. Okay, so in this slide this is an example of buck converters. This is an asynchronous buck converters, doesn't employ any MOSFETs, and this is Vin, and it is a diode, and this is one inductors. So we'll discuss the working of this section also. If we turn on this, the switch turn ons, then the current would, right, the current would increase slowly, right, the current would increase slowly, whereas if it's get turned off, the current would reduce, but it will reduce slowly. So that is the change when we employ an inductor, and we will understand it in the next slide. And this is simple boost converter. So in the buck and the boost you can see the difference. The switch is here, and here the switch is here. Okay, and the diode is employed over here, whereas the diode is employed here. So that is the basic configuration of a buck converters and a boost converter, and I have tried to list them out that maybe you can see the circuits in various kind of electronic devices. Right now we are concentrating on buck converters, but in various electronic devices you might encounter this inverting topology and the transformer flyback topology, and this is employed in SMPS. Maybe this course is not about SMPS, but I have a separate course where we are talking about designing an SMPS and designing an adapter. Okay, so let's summarize what we have discussed till now in this class. And so why we use switching regulators here. So the first point that we discuss is switching efficiency is better in a switching regulator because less amount of energy is consumed, or it is less amount of energy is wasted. Okay, And the third is energy stored by inductor in switching regulator can be transformed to output voltages that can be greater than input or can be less than input or can be inverting than input, which is not possible in a linear regulator, because linear regulator reduces voltage through resistors. Okay, but the question is, if switching regulator is so efficient, why there is need of linear regulators? There is a need of linear regulators because, as we have spoken, that in switching regulator we require two MOSFETs, one inductor, one capacitor. It will create a lot of noises, and these noises can interfere with the data flowing across the various communication buses, right? So we don't want to interfere those things. So linear regulators provide less noise and have a higher bandwidth, whereas a switching regulator doesn't have a higher bandwidth. Okay, so let's go to the next slide now. Let's understand how does a switching regulator work. This is, as we have spoken, this is a boost converter, not a buck converter. Okay, this is a boost configuration. So what will happen? Suppose, let's take the case, this switch is on. This switch represents the MOSFETs in a regulators, because MOSFETs acts as a switch. Here, this is a basic block diagram of a switching regulator. We are trying to understand the concept behind it, and we'll use this concept when we are going to study the data sheet of 3.35 volt regulator IC. So what will happen? If the switches gets closed, the current will flow over here. The flow of current across this inductor would be large, but this inductor will block the flow of current, and it will not rise like in instantaneously. It will rise slowly, but the rise of current will be positive, so the current is rising. Okay, let's suppose the case when this switch is off. In that case, the current would flow across this. As we know, capacitor will try to reduce the flow of current, so the flow of current would decrease. Okay, we'll see in the next slide. This is happening over here, but the entire time, the time at which the current increases and the time at which the current increases, this entire time is called duty cycle. Okay, the entire time is called T, complete time. Okay, and this complete, if we calculate a formula, basically in this steady state operation, the average voltage across the inductor would remain 0 in the entire switching cycle. The average voltage drop across the inductor would be 0. So utilizing this formula, we have got it. We write T on by T on plus T off as a duty cycle. So for just understanding purpose, we'll not go into this mathematics of understanding this thing, but we just have to note over here is that duty cycle is T on by T on plus T off. This is T on and this is T off. T on is the time for which the switch is closed, and T off is the time for this switch is off. So we define T on by T on plus T off is duty cycle, and we calculating this, we have got a formula like V out, that is the output voltage, is V in voltage into duty cycle. This is duty cycle. So if we want a lesser voltage, suppose we want output 2 voltages from a regulator, then at that time the T on would be less, and if we want 3 volt, then the T on will be more, because T on should be more, because we know calculating this by this thing, this is V out is V in into duty cycle, right? V in into duty cycle. So if you check the logic of the lower MOSFET in case of 3 volt, that will give you a lesser logic, whereas if you check the logic of a 5 volt, then it will give a higher logic, because V out is V in into duty cycle, and duty cycle is T on by T on plus T off, and this T on plus T off is constant. So if we change this T on, then the output voltage would change. So if if you have a logic multimeter, always use logic multimeter when trying to repair an electronic circuits like notebook motherboard, right? Because notebook motherboard uses lots of MOSFETs, lots of transistors, and trying to use, if we want to check it, we have to use a logic multimeter that can help us to check very easily. So if you check MOSFETs, the MOSFETs in a 3.3 side of the regulator IC, there you will get less logic in the lower side MOSFET, whereas if you want to check in 5 volt, it will give you more. Okay, because V out is V in into duty cycle, and duty cycle is T on by T on plus T off, and T on is the time for which this MOSFET is closed. Okay, so if you want to get lesser voltages, then T on should be off for a larger time. Okay, and if you want to get more voltage, then T on should be larger. And when we study the notebook schematics, we'll see this switch and this diode is replaced by two MOSFETs, the upper side MOSFETs and the lower side MOSFETs. We are just understanding the basic concepts behind the regulators, and we'll use it to understand the data sheet of the regulator IC. Okay, now there are basically two control techniques. As we have spoken, if we change the duty cycle, we'll change the output voltage. So there are two modes to operate a pulse width modulation regulator. There are two modes. One is voltage mode control, and another is current mode control. See, discussing this thing in detail would require a lot of mathematics like Nyquist theorem. We can plot the various graph, and we can understand what is actually a single loop, what is actually dual loop. I'm not going to do that thing. I'm trying to simplify it in order to understand, in order to basically understand the switching regulators in a good way. Because if we can understand that in a switching regulator, each and every point, then it would really give us a very good idea that yes, this switching regulators works like this. So I'm not going to mathematics. I'm speaking again, I'm not going to mathematics. How is it single loop? How is it dual loop? How a voltage mode control, how a current mode control is better than voltage mode control, but I'll explain it in a very simple way. So there are two techniques of operating a pulse width modulation. In fact, there are many other techniques, but these are the two techniques. These are the primarily two techniques used to operate a pulse width modulation regulators, which are commonly used in notebook motherboard. So we'll go with the voltage mode control, which is perhaps usually used. Okay, in voltage mode control, what happens is the output voltage is feedback to the input to check the error. Okay, and we have a V reference. Like we already know that a 3.3 voltage regulator has to generate 3.3 volt. We already know a reference. So if there is any difference in the output due to if the notebook motherboard requires more current, then voltage would get dropped, right? But we have to fix this voltages, so the error will get feedback to the input, and that would change the pulse PWM. Like here you see the output voltage is compared with a V reference with a comparator. That V error is fed to the PWM modulator, where these things are present inside the regulator IC. This part is present inside the regulator IC, and that regulator IC will then generate drive high and drive low at the upper MOSFET and the lower MOSFET, right? That will generate drive high and drive low at the upper MOSFET and the lower MOSFET. But what time it will generate drive high, what time it will generate drive low, at till how many seconds it will have drive high, till how many second drive low will high, this all will depend on this feedback error, right? This V error, and this V error comes from comparing the output voltages, and it will give an error signal. It will get fed to the PWM, internal PWM modulator present in the regulator IC. That will generate a signal, the gate drive signal, and that will control the turning on and turning off of the MOSFETs. So if we go with the mathematical analysis of this voltage mode control, this is basically a one loop control, because we are trying to compare an output voltage. We are not trying to see the current over here. We are not trying to check, or we are not trying to basically control the output current. We are just trying to control the output voltage. So this is a voltage mode, and I have written a transfer function. I'll not explain transfer function over here, because transfer function is again a very engineering term, and I've just written a transfer function is basically is of second order. And if we talk of current control, that is a transfer function is of just single order. That is more simplistic. Here we are just analyzing the output current. We are trying to control the output voltage, not trying to control the output current. But in the next slide, here in the next slide, this is current mode control. Here the output current is also fed to a comparator. This output current and the V error. The V error was the previous slide. This V error, the output minus V reference, okay, and the current. These two things are compared to generate the gate drive signal, that is drive high and drive low, and that this is a dual loop control. In this case, we are trying to control the output voltage and output current. Not only voltage, we are trying to regulate both output voltage and output current. Okay, so this is better. In fact, okay, this type of regulators are better, because we are trying to regulate the output current and output voltage. Why this is better? This is better because it will help not to increase the lot of current, lot of output current that may hamper the afterward components. Okay, because if we do not control the output current, that may hamper the devices where this current is going on. So this kind of regulators are better, because they are trying to control the output voltage and output current. Okay, so let's see over here. As I said, this is voltage mode control, and this is an example of voltage mode control. Here the output voltage is compared with a V reference that generates V error. This V error is fed to a comparator, which input is a ramp oscillator. It will compare this ramp, and this error is getting compared, and it generates the V switch, which will turn on and turn off this switch. Here we are just representing only one switch and one diode, but this diode would also be replaced by a MOSFET, and if both sides are MOSFET, these are called synchronous regulator. Whatever we are discussing is asynchronous regulator, because we are using just one MOSFET and one diode. These are asynchronous regulator. But in a notebook motherboard, we have synchronous regulators. Both the switches are MOSFET. It is not necessary to have both switch as MOSFETs. We can have one MOSFET replaced by a diode to act as a regulator, but that makes it as a asynchronous regulator. Okay, so this is an example. The output voltage is compared with a V reference. It will generate a V error. This V error is basically compared with a ramp oscillator, and that will generate a V switch. Now where this ramp oscillator is, these are all inside the regulator IC. Okay, inside the regulator IC, that will generate the gate drive signal, that is drive high and drive low. This is a voltage mode control, because we are trying to regulate only a voltage. And an example is MAX 1932. This MAX 1932 is an example of voltage mode control. This is COMP. What is COMP? COMP is basically, this will output the V error. Basically this will output this one. This, it will output this one over here. Okay, so this is an example of voltage mode control, and max 1932 is basically a simple boost regulator. And here we can see the output voltages. The output voltage is feedback to this max 1932, and this is DAC out. That is, inside this max 1932 there is a digital to analog converter that will set the output voltages. So if this output voltage and the DAC output voltage is same, there will be no current flowing across it. Okay, and the feedback, there's a feedback going over here. Okay, there's a feedback going over here. So this feedback will be compared with an internal comparator with a reference voltage of around 1.25 volt, and that error would be over here, pin number 8, comparator, because the error is having a high output impedance that will basically act as a current source. And we will understand this comp pin, because if you see the DV2000 schematic, and if you see the 3.35 volt regulator IC, you will find COMP pin. Let's see the schematic diagram of the DV2000, and there will understand. Over here you see comp 1 and comp 2. So what are those? Basically? Comp 1 and comp 2. This comp 1 and comp 2 are, as I have spoken over here, that it's not necessary to understand this thing, but if you understand each and every pin, it would be really very good. So what exactly is comp? Comp is basically generating the feedback voltages, that is the voltage which is sensed over here, which is compared with an internal comparator having a reference voltage of 1.25. That V error is coming over here, V error, because this V error is having how high output impedance. That is anything that is having high output impedance can act as a current source. So if we change the value of this R7 and C4, then we can increase the loop gain. We can basically increase the loop gain. So similarly, if we change the values over here, if we change the value of this resistor, we can change the loop gain. Loop gain is basically the overall gain. As we have seen, as I have told, that in the voltage mode control there is only one loop. We are trying to control the output voltage, not output current. So this comp 1 and comp 2 will basically output, this is an output pin. It will basically output the error. Okay, error, V feedback minus a reference voltage, and it will be output at this pin, that is comp 1 and comp 2. So let's go back again to what we are discussing till now. And yeah, max 1932, and we have discussed over here there is another type of control, that is current mode control, where we try to control the output current also and output voltages. And how do we current? We sense the output current. And that sensed output current is compared with an internal comparator, this current and V error, and that error will try to drive internal PWM pulse width modulation, and that will produce gate drive signal, that is drive high and drive low, over here you see, over here drive high and drive low. So this drive high and drive low is generated through over here, through an internal arrangement, that is comparing the V output and the output current, that is dual loop. And normally in a notebook motherboard we have a regulator which are operating in current mode, those which are trying to control the output current and those which are trying to control the output voltages. Okay, so and this is an example, as I said, that the current mode control is a dual loop. How dual loop? One that is controlling the output voltage and one that is controlling the output current. Not going into mathematics. Mathematically it can be proved that it is a dual loop, right? But we're not going into that mathematics. You can just analyze this is one loop and another is second loop. What is the first loop? First loop, it is trying to control the output voltage. Second loop, it is trying to control the output current. So current mode regulator is better, and those are used in notebook motherboard. Here this is the example. You can see this output voltage is compared over here, that is generating V error compared with the V reference, and the current sensed. You see a resistor is there in the path of inductor that will sense the flow of current. More current, more drop, less current, less drop. So that will be sensed and it will convert into voltage, and this is compared with a regulator that will generate a signal to drive an RS flip-flop. You know what is RS flip-flop? Just remember, if in RS flip-flop R is 1, value would be 0. If R is 0, value would be 1, right? RS flip-flop. R means reset, set means set. So if R is 1, value would be 0. If R is 0, value would be 1, right? So this V error and the current is compared to generate a signal over here, right? Generate a signal over here, and this it will generate a signal, and that will compare with a pulse oscillator to generate the V switch that will drive the external MOSFETs, right? External MOSFET. Here in all the examples I'm showing, those are all asynchronous switching regulator. Asynchronous switching regulator means there is only one MOSFET used and another is diode, whereas in a notebook motherboard synchronous switching regulators are used, and they are better, and we will discuss why synchronous switching regulators are better. Why I'm trying to discuss all these things is to understand switching regulators in a better way. Till now what we have discussed, switching regulators are better than linear regulators. Switching regulators can be operated in two ways. One is the voltage mode control, another is current mode control. In voltage mode control, we are trying to control only the output voltage, whereas in a current mode control, we are trying to to regulate the output current and the output voltage. There are two types of switching mode regulators. One is synchronous, another is asynchronous. In a synchronous, we use only one MOSFET and one diode, whereas in a synchronous switching regulator, we use two MOSFETs for two switch, where in asynchronous we are using only one switch. Okay, and having two switch is better. Okay, so this is an example. Max 668 is basically current mode switching regulator, and these are the control techniques as we have seen over here. As I was talking about, actually I have a little pain in my teeth, so I'm not able to speak in that way, so I think some of the words cannot be understood by students, and they have to basically rewind the videos to understand it. I'm having a little pain, and that's why there has been so much of delay in preparing these videos and giving to the students, but the pain is quietly healing up. So in the next coming days, those videos will be very frequent, and I'm trying to complete this course by 15th of August, because after that we have another course on tablet and mobile repairing, and we'll start those courses also. Okay, so in this coming weeks, the videos very often, and I'm trying to complete the videos as much as possible, with maximum recording of practical classes, also with analysis of sample problems like no display, dead, BIOS problem. How do we analyze this is a BIOS problem? How do we analyze this is a display problem? The real cases that we experience in our service center. Okay, and we'll try to solve those problems with whatever things we have learned over here. No heat and trial, analyzing everything from very basic. Okay, so as we have spoken, there are two types of regulators. One is asynchronous switching regulators, another is synchronous switching regulator. So in a notebook motherboards we have synchronous switching regulators. We are using two MOSFETs for a switch, but as I said, it's not necessary to have two MOSFETs. We can replace one MOSFET with a diode, but do not try to use that. If you understand what I have spoken till now, then you can do this, no problem. But if you do not understand, if you're just understanding the crux, then do not do this. Just replace this with MOSFETs. We'll also talk about the cases of sorting. How do we check which thing is sort? How do we check the whether 3.35 volt regulator is sort? In many cases, you'll find this IC to be sort, but we'll check how it is sort. Okay, once we covered the things up to certain level, once we finish the power level, once we finish the supply up to the CPU level, then we will discuss these things. So in a notebook motherboard, a synchronous switching regulator is used, and this is skip mode. The skip modes are present in some of the regulator IC. What exactly is a skip mode? If our output voltage is fixed for a certain time, there is no disturbance in the output voltages, then the gate drive and that is the gate drive pulse can be switched off for some time. We can skip some cycles. Okay, we can skip some cycles, right? That is skip mode. Skipping some cycles of the PWM, that is skip mode. It is basically used in light load. Where light load means when there is a less requirement of current, when we are not using graphic intensive program, when there is not much pressure on 3.35 volt to generate a greater output current. Okay, that is skip mode. Not necessary. Efficiency, as we already skipped, skip mode is used for efficiency. So now we have understood the switching regulators, and now we'll go into the data sheets of the two switching regulators used in the Lenovo Y570 and another used in DB2000, and we'll try to understand each of the pins. Please note, I've discussed the things why these two diodes, why these two MOSFETs are used, and we have discussed the type of control techniques. One is the voltage mode control techniques, another is current mode control techniques, and we have also discussed the block diagram of all of them. So we'll go back to the data sheet and understand the data sheet using this concept. Okay, so till now we have discussed the basic concept of switching regulators. We have understood how does the switching regulators work. Now we are going to see how does the RT8206L or the TPS51120, which are present as voltage regulator in Lenovo Y570 and DB2000 respectively, works. Why we have studied the previous thing, how does a switching regulator works, because we want to understand these two chips in a very great way. So now while we were discussing each thing in this data sheet, the most important things in this data sheet to understand what are the important pins in a switching regulators, that is 3.35 volt regulator IC. So RT8206L/M, this is used as a 3.35 volt regulator IC in Lenovo Y570. It's written L/M. Why does it? Why it's written L/M? Let's check. Actually, the numbering of this IC is L means with SECFB and M means without SECFB. What does this SECFB means? We'll discuss it later on when we are discussing each of the points. and this box, it means if it's G, then it means it's green, that is lead free, and if it's Z, it's leaded, not lead free. And here QW, it represents the package type. Okay, so and it's written RT806L/M dual step down switch mode power supply. Dual means two voltages coming from one switching regulator, and here it's generating 3.3 and 5 volt. Okay, it's also written RT806L/M includes two pulse width modulation controller fixed at 5 volt/3.3 volt or adjustable from 2 volt to 5.5 volt. So that means this switching regulator can work in two way, right? You see over here, it can work in two ways. One as fixed, when we want a fixed 3.3 volt, when we want a fixed 5 volt, then this feedback FB1 and FB2 is grounded. Either may be grounded or it may be attached to VCC. So if this FB1 and FB2 is attached to ground or connected to ground or VCC, that means this switching regulator is operating in a fixed way, that it has to generate 3.3 volt, it has to generate 5 volt. That is, if you measure by multimeter the voltage over here, it would be always be 3.3 volt, and if you measure with multimeter over here, it always be 5 volt in fixed volt, in fixed way, when this voltage regulator is actually operating in a fixed way. But sometime you must have noticed, when you measure by multimeter, the value is approximately not 3.3 volt. It is somewhat less, 3.1, 3.2, 3, right? 3.1, 3.19. If you measure voltage over here, it may give you value like 4.9, 4.8, but that doesn't mean this switching regulator is faulty, because the switching regulators, it also works in a adjustable manner. You see over here, adjustable voltage regulator. In that case, your FB2 and your FB1 is connected over here. So how to know whether this regulator is working in a adjustable way or a fixed way? We can see the schematic. Let's see the schematic. Here in the schematic, you see FB1. This FB1 is connected. That means this part is working in a adjustable way. That is, if you measure the voltage over here, sometime it might give you values less than 5 volt, little less than 5 volt. That doesn't mean this switching regulator is faulty. Okay, but here in the schematic, you see over here, this 32 pin number is basically FB2, feedback 2. If you see over here, if you see in the data sheet, 32 pin number FB2, yeah, FB2. But here in the schematic of Lenovo Y570, this RE, it is denoted by REFIN2, that is feedback 2, is connected to VCC, right? Because VCC is also connected to this, so it's connected to VCC. That means it is working in a fixed way. That is, if you measure voltage over here, it will always show you 3 volt, right? 3 volt, not less than that, not less than that. So you got my point? How to check whether this switching regulator is working in an adjustable way or in fixed way? We have to check the feedback pin, FB1, FB2. Here in Lenovo Y570, they have denoted FB2 by REFIN2, because FB2 is connected with a reference. That is, this part is working in a fixed way, whereas this part is not working in a fixed way. This is working in an adjustable way. Okay, now let's go back to the data sheet and we'll analyze each of the things. Very interesting. These all things can be analyzed if you understand the data sheet, each things properly, right? We'll discuss each of the points. And this is the two way that is this switching regulator can be used. One is the fixed way, another is the adjustable way. And let's check the, let's go ahead. Yeah, this is the functional block diagram of RT8206L/M. So this regulator has inside two SMPS1, SMPS2 PWM buck regulator. Okay, this is PWM buck regulator. Another is LDO, low dropout fixed volt, right? And this is SMPS1, SMPS2. So this SMPS2 will generate gate drives. This will generate a gate drive signal U gate 2, and this U gate 2 is generated through this comparator, the inside comparator. This comparator is inside it. You cannot see it, right? This is inside the regulator IC, and this is the boot 2, that is the supply to the comparator, which is generating the gate drive signal for the upper gate MOSFET, and this is for the lower gate MOSFET. This is connected to the PVCC. As we have already spoken, PVCC, very important. What was the first point? It gets Vin, then LDO is released. LDO is connected to the VCC and PVCC. So if PVCC 5V_L, 5V_L is generating through LDO, and this is going to VCC and PVCC. So if VCC and PVCC is not there, then it will not generate the U gate 2 and L gate 2, right? So this L gate 2 is generated by the comparator, and whose signal is generated by the internal SMPS2 PWM buck controller. Similarly over here, U gate 1, U gate 2, L gate 1, U gate 1, L gate 1, U gate 2, L gate 2. There are two MOSFETs connected over here. You see that two MOSFETs connected, DH3, and you see DH3 and LX3. This is LX3 and this is DL3, that is drive high, drive low. That is connected to the U gate 2, L gate 2. Similarly over here, U gate 1 and L gate 1, right? U gate 1 and L gate 1. So here in the data sheet we are checking, there are two internal SMPS1 PWM buck controller, right? One is generating the 3.3 volt, another is generating 5 volt, and how they are generated? Through controlling the turning on and turning off of the external MOSFET. And to control the turning on and turning off the MOSFET, the U gate 2 and L gate 2 is generated. And how U gate 2 is generated? With this comparator with boot 2 and phase 2 input, right? And there is an internal LDO. You see, there is internal power on sequence. Internal power on sequence. If we go to the data sheet over here, they will clearly write it in the very first page. You can see each thing has to be minutely written. You see over here, they will write something related to this. Yeah, RT8206L/M includes onboard power up sequencing, power good outputs, internal soft start, internal soft discharge. What does this means? What does this means? Onboard power up sequencing. What does this means? Internal soft start. What is soft start? Power up sequencing means, you can clearly see over here in the functional diagram. You see the functional diagram, and I think the functional diagram is on page number 5. So you see the power on sequence. This is connected to the enable LDO EN1 and EN2. That is with this is the logic inside this regulator IC, which will determine whether to generate 3 volt, whether to activate this SMPS1, whether to activate this SMPS2. So the logic, the power on sequence logic is inside, which gets started with en1, en2 and enable LDO, right? And what is soft start? Okay, so let us see what is internal soft start and why is it required. This is actually my my handwriting. I do not find time to basically make it in PPT. So in this diagram you can see this output voltage is connected to the amplifier, which is giving you V error. So suppose at time when we start a circuit, suppose when we start notebook motherboard, then in that case this output voltage at the starting would be 0, right? So if this would be 0, then this V error would be too much, and if this V error it would be too much, this will generate pulses very often, and that will lead to a very high charge current, very high current flowing over here, and this high pulse may damage this transistor or MOSFETs connected over here. If we see in the schematic, it might damage this MOSFETs, because at time t is equal to 0 this voltage is 0, so this will give a feedback over here, and this will generate very high pulses, this high drive DH3 and DL3, and that might damage this MOSFETs and the components which are connected to the 3V CPU power line. So we need to slow down this V error. So that's why an external capacitor is connected. You must observe some previous circuits, some previous voltage regulator where an external electrolytic capacitor is connected, but it is costly to connect an external electrolytic capacitor because the assembling cost would also increase. So nowadays this type of voltage regulators are coming where there is an internal soft start, right? Internal soft start. And what is internal soft start? We'll see another picture over here, and this diagram is basically representing an internal soft start. Here we do not use any external capacitor, which will save assembling cost, right? And here what we have used is, we have basically used a current divider which is giving a less value over here, hence not producing that much pulse initially and saving this transistor. So we'll not go into details of this circuit, but we have to understand that nowadays internal soft start is there, no more external capacitor is used. And what is soft start? We have already understood what is soft start. Soft start is that when output voltage is 0, we need to generate pulse slowly, right? We need to generate those pulses slowly. Okay, so we'll go back to the data sheet and understand each of the points in the RT8206LM. So this RT8206LM is having two SMPS1. This is SMPS1, SMPS2, boot 2, phase 2. This is the supply for the internal comparator to generate the U gate 2, which is basically the gate drive signals to the upper MOSFET. Over here you can see, over here this signal is generating the DH3 that is connected to the U gate 2. Okay, U gate 2, and this is L gate 2, and L gate 2 is connected over here. L gate 2 is connected to the lower MOSFETs. Okay, and so we have, and this is the basically the PWM part inside the RT8206M, and this is one time one shot trigger that is generated by the PWM. This is the internal logic. This part is the internal logic. We don't have to go into this detail, and now we'll cover the details of each pins of this regulator IC. So let's go to the each pin. reference. This is pin 1. So let's go to the schematic and see what does it represent. Reference, and reference is connected to 5V underscore AL, right? 5V underscore AL, which is generated through the LDO when it gets enable LDO. And how does it gets enable LDO? Some part of V in voltage is fed to the enable LDO, right? After it gets enable LDO, LDO is generated 5V underscore AL, and this 5V AL and 5V underscore AL is connected to the reference, right? So this reference is basically, it can source up to 50 microampere for external loads, right? This is T on. T on is pin number 2. So let's see, this is T on pin number 2. So what does T on pin is function is? T on is frequency select input. That is, we want to fit the at what frequency this regulator has to work. So if T on is VCC, then it will work at 200 kilohertz to 300 kilohertz, and if T on is a reference, then it would work at 300 kilohertz or 400 kilohertz, and if T on is ground, it would work at 400 kilohertz or 500 kilohertz. So in this schematic of Lenovo Y470 570, this T on is grounded. That means here they are working as 400 kilohertz to 500 kilohertz. And let's see VCC. VCC is the analog supply voltage in input. You can see in the functional diagram VCC. VCC is going to the PWM core, right? PWM core. So VCC is going to the PWM core, and VCC is also connected to the 5V underscore AL. So these are the important pins, right? These are the important pins. And ENLDU, enable LDU, this is 4 number. This is connected, a part of V in is fed to the enable LDO, and if it gets enable LDO, then LDO would get generated, right? Then LDO would get generated. Otherwise, if you see in this over here, if this resistance is faulty, or if this resistance is faulty, then correct enable LDO would not be fed, and in that case no LDO would get generated. So we have to check these resistors, okay? And let's go V in, as we have already spoken, V in is the power supply input, and similarly DC bat out is the power supply input in DV2000, okay? And the linear LDO we already understand. And there is one more important point to note over here, is that if you see over here, if the output voltage, that is the LDO, would get fed by BYP after you see, after this part, after this 5 volt stabilize, that is, after this 5 volt stabilize, the internal LDO gets shut down, and this LDO voltage would be generated through this BYP, and BYP is connected to the out 1. And where is out 1 connected? Out 1 is connected to the output. So if this voltage stabilizes, then this LDO is get fed by BYP, and we can see over here this BYP is connected to the LDO, and there is a switch hold threshold, and this is determined by the internal logic, okay? So let's find about the other pins. LDO we have already covered, and this is BYP, that is switch over source voltage input for LDO. That is, if the voltage external V out 2, that is 5 volt stabilizes, then the LDO is connected to the BYP, and this is V out 1. V out 1 is, what is V out 1? V out 1, this is V out 1. You see over here, out 1. This is connected over here. So as we have already spoken, that this regulator operates in two ways. This part is working in a adjustable because the feedback is connected, right? FB1 is connected, whereas here this feedback REFIN2 feedback is connected to 5V_AL, that is, it is connected to the VCC. If it's connected to VCC, then it will work as fixed, right? It will work as fixed. So in this case, Vout1 is SMPS output voltage sense input, and FB1 is SMPS1 feedback input, because this internal SMPS will require feedback, even in two operations, that is, one in fixed operation and another in adjustable operation. It will require feedback. So if the FB1, that is here in the schematic diagram, we'll go to the schematic diagram. Here this FB2 is connected to VCC. So who will provide feedback? This will provide feedback. See, this Vout2 is connected to the over here, the feedback. It's giving feedback to the this part SMPS. So there are two pins. One is Vout, another is feedback. Vout is for providing internal feedback to the PWM inside this IC, and feedback is like, if we are not using feedback, then it will operate in fixed manner. If we are using feedback, it will work in adjustable fashion, right? Okay, so let's go see the other pins. And ILIM1, this is SMPS1 current limit adjustment. We can adjust the SMPS1 current limit externally by this pin, right? And here these pins are ILIM1. You see, this is grounded and this is grounded, right? This is grounded and this is grounded. And power good 1, this all regulators supply power good which are connected together to give feedback to the IO controller. We can see in the schematic, this will generate power good 1 and power good 2. So this is POK1, that is power OK1, and POK2, power OK2, and this power good will we get converted to H power good, which is fed to IO, right? And as we have spoken in the third class, that all regulators supply power good which will eventually goes to the PCH, and which will eventually go to IO controller, except VRM, which generates power good directly to the PCH. Okay, so let's see the other pins. EN1, here you see EN1, enable 1, where is this pin? And EN2, where is this pin? We can search over here. 3V, 5V_EN. So where would they get? So they are getting connected to the 5V_AL. And if we see DV2000, this EN1 and EN2 are fed from the IO controller and PC and ICH, where in Lenovo Y470 or 570 we have no such. It is internally fed. That is, this IC will generate the switching voltages. Once it gets V in and enable LDO, this will generate this switching voltages. This switching SMPS inside this SMPS inside the RT8206 will get started when it gets V in and enable LDO, right? But in DV2000, this enable is generated by IO and ICH, right? And there are in fact 4 enables in the DV2000. These two are not connected, and we'll see when we are seeing the data sheet of DV2000 what is the significance of this. Okay, so let's complete this data sheet of RT82061. Enable 1, UGate 1. UGate 1 is the high side MOSFET floating gate driver. Here UGate 1, you see UGate 1, UGate, this is drive UGate 2 and LGate 2, and UGate 1, this is UGate 1 and LGate 1. So these are the driving signals for these MOSFETs. Okay, these are the driving signal for these MOSFETs. And boot 1, boot 2, boot 1, boot 2, you see over here boot 1, boot 2, this is boot 2 and phase 2, that is the source for the internal comparator which will generate the signal UGate 2, and for LGate 2 we have PVCC and ground. So that's why PVCC is important. If you do not have PVCC, then this LGate 2 won't generate, and so the lower side MOSFET won't work. So let's see over here VCC, this is VCC, and here you will find PVCC, right? So both of this pin would have LDO voltages, and PVCC is important because PVCC helps to generate DL3 and here DL5, right? You see in the block diagram DL3 and DL5, because this part generates the LGate 2 and LGate 1. So this is connected to the PVCC, right? PVCC, and the phase is the phase 1 and phase 2 is the lowest supply for this comparator. Okay, so we see the other pins. FV1 and FV2 we have already discussed. LGate 2, boot 2 we have already discussed. EN1 and EN2. SECFB, as we have already discussed, RT8206 LM or L or M. So what does this means? SECFB, we see over here in the very first page. If L, that means it is with SECFB, and if it's M, that is it is without SECFB. So we'll see what does this SECFB means. In SCFB it is charge pump feedback input, that is the SECFB is used to monitor the external charge pump. So RT8206L is having SECFB enabled, whereas RT8206M is having SCFB not enabled. Okay, and skip we have already discussed. Skip is for the skipping pulses during light load condition. When there is a light load, the skip mode is entered. Okay, and ILIM2 we have already discussed. Vout2 is similar to Vout1. So now we'll discuss the data sheet of TPS 5.120, and we'll see what are the differences between those two data sheet and the implementation. Okay, okay, so now we'll see the data sheet of TPS 5.120, and this is the 3.5 voltage regulator used in DV2000. And if you see in the data sheet, it's clearly written it is a highly sophisticated dual current mode synchronous step down controller. We have already discussed what is current mode, what is voltage mode. In voltage mode only output voltage is controlled, whereas in current mode we are also controlling the output current, right? So it is in this line it is very similar to the RT8206M. Alright, and if we see its more detail, let's go back, let's go directly to its pin details. Okay, page number 8. Yeah, this is comp 1 and comp 2. If we see the schematic, this is comp 1 and comp 2. This comp 1 and comp 2 was not present in RT8206LM. So what are this function is? If we see, it's written loop compensation pin, connect RC from this pin to ground for proper loop compensation. And what this is exactly is, this comp 1 and comp 2 is basically this part, right? This is comp 1 is connected over here and comp 2 is again connected to this is basically giving the V error. This comp 1 is internally connected to the V error, whereas comp 2 is also connected internally to the V error 2, because there are two SMPS inside it. So they basically act as a current source, right? They basically act as a current source. All right, comp 1 and comp 2. Here you are seeing 4 enable pins. First one enable pins is connected to the ICH, EN2 is connected to the IO, and enable 3 and enable 5 are meant for LDO, and there are two LDO, V regulated 3 and V regulated 5. So how this enable 3 and enable 5 are determining this LDO voltage? We go to this the data sheet. In the data sheet it's written enable 3 V regulated 3.3 low dropout linear regulator enable pin, and connect to ground to disable, float or tie to enable. So here if you in the schematic you see this is not connected, that means the LDO are enabled, and if it's get connected to the ground, this LDO would get disabled, no LDO would come, and hence the entire circuit won't work. Alright, because this 51120_V field is generated by 5V_AUXS5. Alright, so this won't generate if this accidentally gets connected to the ground, and if it's not connected to the ground, these are enabled. So if this IC gets the DC bat out, then V regulated 3 and V regulated 5 will turn on, and here you can measure with multimeter 3.3 volt and 5 volt. And if you're not getting 3.35 volt, check these two pins, enable 3, enable 5, whether they are getting to ground. If not getting to the ground, then your IC is faulty. Okay, then your IC is faulty. So we'll go to again to the data sheet, and we have all CS1 and CS2 is current sense comparator input. This part was also not available in RT8206L. So let's see CS1 and CS2. This is CS1 and CS2 again connected to the 51120 FILT. Okay, let's go again. And enable we have already discussed. P ground, P good 1 and P good 2 is similar. Power good 1, power good 2. You see over here, power good 1, power good 2. And where this power good is going on? One of the power good is going to the CPU_on. So here this is different than RT8206L. What are the differences? One enable pins, another the power good. This comp 1, comp 2 was not present. Okay, there are 4 enable pins, whereas there are only 2 enable pins, and the LDO gets auto started. Okay, LDO gets the switching voltage gets auto started. This was auto start in the previous regulator that we discussed. Here you see in this data sheet, no enable pins to start this switching part, this SMPS2 and SMPS1, whereas in DV2000 you require these signals to start the internal SMPS. So these are the basic differences, and we see V out 1, V out 2 almost same, no difference between them. You see there are no difference between them, but here and V regulated 3 and V regulated 5, these are the 2 LDO, whereas In RT8206LM there was only one LDO. Okay, so we have covered the data sheet of both of these regulator IC, and we have seen the differences between them. And the major differences are basically there are 4 enable pins where there are only 2 enable pins. The switching part was the switching SMPS, internal SMPS was auto enabled in the RT8206LM. And why these are differences? These differences are basically due to differences in power sequencing, due to the use of ICH in DV2000, and due to use of PCH in Lenovo i3 Y470. And we'll discuss all about this switching power sequence in the next class before we start IO controller. So I think for now on we are pretty clear about the switching regulators, and in the next class we're going to cover the IO, and before that we'll have the ACPI, understanding the power sequence. Thank you. Okay, good morning everybody, and welcome to this class. There has been a lot of gap between our previous class and the today's class and I've tried this time to compile all the things that is related, because the today's class is the most important class of IO controller and BIOS. So in this class we'll look at how does IO controller works and how does it communicate with BIOS, and what are the different architectures present in notebook motherboard. But in the today's class I'll just go through the Lenovo Y470 and Lenovo Y570, and I'll cover the remaining things a little bit later on, and I'll share with all of you one slideshow which I have prepared of around 200 pages describing the complete working, and I'll request you to go through that PowerPoint presentation of 200 pages, and then we can discuss that PowerPoint presentation, because for an urgent reason I have to move to Hong Kong, and that is very emergency. So I will just discuss about the working of IO controller in the Lenovo Y470 and 570, and I'll share the slideshow of 200 pages, and you're requested to go through that slideshow, and then after a week we will discuss the entire slideshow, and I think that would be better. So let's just start with the today's small class. Okay, we have already covered all those things, and let's go back to this. We have already covered 3.35 volt generation, the various regulator IC, VIN generation, and the 15 volt generation, the Lenovo Y470. So today's class is this. As I've already discussed in the digital circuit framework, that any electronic IC requires 3 things, that is supply, reset and clock. And here in this circuit you see this the IO controller used in this notebook motherboard is IT8518. So for any IO controller you can see these are the supply pins: V standby, VCC, VBAT, AVCC and VST VBAT. When we discuss this IO controller in the greater detail, we'll also speak of the power planes. What are exactly power planes? There are various power planes present in a notebook motherboard, right? There are various power planes. So what we will do is, what are the important powers here for this IO controller? This 3.3 V underscore EC, the one which is connected to V standby, because this IO controller is turned on even when you do not press power button, right? So when you don't press power button, this IO controller is turned on. That means the power has reached to this IO controller. So the power which is connected to the V standby of IO controller is the most necessary power. Okay, is the most necessary power. So let's see how does it generate. We have already seen 3V PCU has already been generated in the previous stage. So it is passing through a registers to convert into 3.3 V underscore EC, which is fed to the V standby pins. Okay, so that supply has already been reached. Now let's talk of reset. So here this 3V PCU through a resistance is going to as a reset. Okay, this is also called EC reset. So supply reset has already been reached. Now is the clock. See, there are two kinds of IO controller. One in the previous board, one external clock is required for a clock, but in a newer kind of board, maybe that external clock may not be required, or maybe it may be inbuilt. So this IT8518, if it is if its inbuilt clock module is used, then it won't have external crystal. Okay, it won't have external crystal, and if external crystal is used, then that external crystal would be present on the notebook motherboard. So there is a problem, like if there is no external crystal present, how do we check that the clock has reached the IO controller? That is a major question. Well, we know this BIOS, the SPI BIOS is connected to the clock generator, so we can check at this pins. The pin number 1, that is SCE, serial clock enable. If there is a waveform coming over here, that means the internal clock of the IO controller is working. This we can check for if there is no external clock present, no external crystal is present, because in a newer kind of board you won't find the external crystal, okay, because it is having inbuilt clock module. So in that case we have to check this pin, the pin number 1 of the SPI BIOS. Okay, if there is a waveform, that means we have to use oscilloscope to check the waveform, right? If there is we have to use oscilloscope, and in my oscilloscope class I'll show the various ways to check these signals, that is the clock signal of the BIOS and the IO interaction, the LPC bus, the DMI bus, we'll check X bus, we'll check all kind of the signal. The ADS has strobe, that is ADS has is the first signal that is generated by the processor. So if we are able to locate the ADS has, then we can say that processor has worked okay. Okay, the processor has worked okay. So we can check all the signals through oscilloscope, and in my oscilloscope class we'll discuss about all of these things. Okay, we'll discuss all about these things. And so this EC, for we are talking EC is the embedded controller that is present inside the IO controller. See, the IO controller has many functions. We'll discuss once I share that 200 pages slides with you. You go through that slide, and then we'll discuss what is IO controller. The IO controller has many working. Okay, it has got many modules. So the EC has received 3 things: supply, reset, and a clock. And now the EC will start reading this BIOS. Okay, the EC will start reading this BIOS. Here we have still not pressed the power button, but EC has started reading the BIOS. Okay, so because it has got all the 3 conditions: the supply, reset, and clock. Okay, supply, reset, and clock. Okay, so till now we came to know that EC, embedded controller, requires 3 things. Okay, supply, clock, and reset. So let's see the next part. Okay, I'll be trying to cover the entire embedded controller, but if I do not find time, then meanwhile I'm sending you the PPT, the PowerPoint presentation. Okay, so but I'll try to cover this PowerPoint presentation even though I'm in China, and I'll cover the videos as fast as I can. Okay, so the supply has already reached. Okay, and this is EC reset. As we discussed in the digital framework, 3 things important: supply, reset, and clock. And I spoke, like in the newer kind of boards, we have embedded the IO controller, which does not require external crystal because they have built-in clock module. Okay, so that external crystal may be present or may not be present. If suppose they are not present, then where we can check that whether this IC has received clock or not, then we can see over here on this pin, okay, on this pin, the U19, okay, EC BIOS U19 pin number 1, that is clock enable. At this pin with oscilloscope we can measure the waveform. If there is a waveform, that means this IO controller is receiving its clock signal, okay. And after receiving these three things, the embedded controller will now start working. It will start interacting with the EC BIOS present in the flash chip. We'll discuss later on that there are three kind of BIOS chip: EC BIOS, system BIOS, ME BIOS, and how they're interacting, all of them, okay. So now they have the embedded controller. Inside the IO controller has got three things. So now the EC will start interacting with the BIOS, that is, it will start booting up, right? It will start booting up. Let's see, okay. So see, there is now it will generate 3V underscore S5 and 5V underscore S5. See, there are two scenarios. One in which we have notebook motherboard with battery connected, okay, and adapter also connected to the power supply. Then another case we have battery out, okay, and only adapter. So if this motherboard is not having battery, it is only having adapter, then this S5 on signal will get generated without pressing power button, okay. Two scenario, it will get generated without pressing power button, and if there is no adapter and only battery, then this S5 on signal will get generated after pressing power button. You must have experienced many scenario like notebook motherboard auto start without even pressing power button, right? These are all basically cases of CMOS battery. I'll explain this scenario, that how does a notebook motherboard know that it is without battery or it is with battery. This signal, this AC in, as we have studied AC in, the AC in signal will determine whether AC in or AC present, right? AC in, DC in, those signals will let the IO controller understand that yes, it is with adapter or without adapter, okay. If it is with adapter, then you have to press power button to generate this S5 on. If it is without adapter, it is only with battery, then you have to press. This is all done to prevent the power loss, to prevent this power loss. We see over here this IO controller will generate S5 on, okay. As you already spoken, these are all parts of ACPI, and I will have a separate lecture on ACPI, how does the ACPI works on. So the ACPI is needed to conserve energy, to conserve power. So this S5 on signal will go to this transistor. Since this S5 on signal is going to the base of this transistor, so this will turn on this transistor, current will flow across this, okay. The current will flow across this. So here this is, you can see this is an N channel MOSFET, okay. This is an N channel MOSFET, and in N channel MOSFET we know for N channel MOSFET we know if VGS is positive, then the current will flow from drain to source, right? VGS positive. But here if you see if this signal, it is getting a sorted path, the entire current will flow across this, right? The entire current will flow across this, the entire voltage will drop because ground would come over here, so there would be 0 voltage. So you can see this VGS would be 0, so this MOSFET will be turned off. So in that case, what would happen? This 15 volt would get connected over here. Okay, this 15 volt, this 15 volt would get connected over here. Now this is again an n channel MOSFET because the arrow is inside, so the VGS has to be positive. So at the gate there is a 15 volt, this VGS is positive, so this switch will turn on and this 3VCP will come over here. Similarly this 5VCPCU will come over here. In this circuit you can check in the circuit. Okay, you can check in the circuit. Wait, we can see I have prepared a lot of material for all of you guys. So, and I'll cover this part because this is easy. Embedded controller is very important to understand, and also the practical aspects to understand, because the various waveform with it. So in the next class I'll give you the slideshow for timing, and just go through that slideshow because that is 100 pager slide, and the 100 pager slide is very, you cannot cover it in just single class, so you have to just go through across it. Okay, so we are going to find out the PQ54. Let's search over here, PQ54, and we find out. Okay, so we'll magnify it, and this is PQ54. Okay, yeah, so this S5 on, as I spoke, S5 underscore on will get generated after pressing power button when battery is inserted, and S5 underscore on will auto generate if adapter is present even without pressing power button. Okay, so this S5 underscore on is generated. It will come at the base of this transistor, as we have spoken. When at the base of the transistor any current flows, and VC is close to, VC is more than, okay, if VCE, base, collector, emitter, okay, base, collector, emitter, so this would be forward bias, and this transistor will get turned on, and so there would be a switch, so this entire current will flow across this. Okay, entire current will flow across this. So here voltage is 0 because this 5VPCU current will flow across this, so there would be 0 because this will turn on, the ground would shift over here. Okay, the ground would shift over here. Since ground is shifted over here, the VGS is not positive. The VGS is not positive over here, so in that case this MOSFET will turn off. This 15 volt would get connected over here, so it will turn both this n channel MOSFETs, and 5V underscore S5 and 3V underscore S5 is hence generated. Okay, is hence generated. So let's see what next. The main important thing is to note the generation of S5 underscore on. The S5 underscore on will be generated automatically if there is adapter. S5 underscore on will generate after pressing power button if there is a battery and without adapter. Okay, so let's see, we have already covered this, right? Yeah, this is basically the power switch, right? This is the power switch, and this power switch, if we press the power switch, what will happen? It will generate a signal NBS on. After getting NBS on, this EC will now issue signals to south breeze. Okay, will now issue signals, the power on signals to south breeze. Without getting this NBS on signal, south breeze will not receive power related signals, and hence the power on process would get incomplete. So we have to press power button to generate NBS on. After getting NBS on, the embedded controller inside the IO controller would generate the power on signals to the south breeze or to PCH. Okay, what is a valid power on signal? A A valid power on signal is a jump to plus 3V, plus 3V to 0 and back to plus 3V. Right now this is at plus 3V, right? This is plus 3V, plus 3V PC. If you measure with multimeter, this is 3 volt over here. But when you press power button, the power button comes over here and the voltage would go down to 0, and then when you remove it, the volt would again become 3V. Okay, and this, and it has to be done in a fraction of second, right? Fraction of second. If you press the power button like up for more than 4 seconds, then the embedded controller would understand it as a shutdown signal, because you see, in newer kind of board, you just have one single button to start, to restart and to shut down. So how does this embedded controller understand that this is an start signal, this is an restart signal, or this is shutdown signal? If you press this power, this all depends on the timing of pressing. All right, this all depend on the timing of the pressing. Each time the ACPI, time is an important factor in powering on board, right? If anything happens beyond time, then the entire process would get disturbed. So here, this, if you keep on pressing this power button more than 4 seconds, then the embedded controller inside the IO controller would understand it as a shutdown signal. Okay, so what we have studied, the main thing is this EC requires 3 things. There are various power plants over here. We'll discuss this power plants once you go through my slide presentation, because now it's very going to be tedious in explaining this. The EC inside the IO controller requires 3 things: supply, reset and clock. Okay, supply, reset and clock. After getting this supply, reset, clock, the embedded controller inside the IO controller is now active. It can read through BIOS. You see, this SPI chip, this flash BIOS is connected to plus 3V PCU, which is already generated. Okay, so it can read through this BIOS, and we can read the data. We can read the data through oscilloscope. If there is a valid waveform, if there is a valid data waveform over here, we'll see how does that waveform looks. Then this process is okay. After, if there is a battery, if the system is powered by battery, then after pressing power button, this S5_on will generate. Without pressing power button, this won't generate in case of battery powered. If it is powered by notebook motherboard, then this S5_on will automatically generate, which will generate this 3V_S5. Okay, now I'll also explain the case of notebook motherboard, where we have like it auto start without CMOS battery. It is start after pressing power button CMOS battery. I'll explain this case in the slide. So for the time being, just go through my slideshow, and I'm coming back going through some research process, and then I'll cover the entire videos as quickly. And sorry for delay, it's getting more delayed than expected, but once again sorry. I'm trying my best to cover this video as soon as possible. Thank you very much. with the initial file, right? You get my point? That is, this embedded controller requires programming after soldering a new IO controller because it has an embedded flash. So we have to change the program of that flash also. So you can see this is a very interesting problem, very interesting case in fact. So I have taken this data sheet as my reference, and whatever concepts that we are going to study, we'll be using these concepts to understand our two reference schematic diagram. That is, one is DV2000 and another is Lenovo Y470 and 570, right? So we will be using the concept studied in this data sheet of this KB9012 IO controller, that is embedded controller, to understand all these things. And in this class we will be discussing very interesting points also, and one of the interesting point is this E-flash, that is embedded flash. You must have noticed problems in some kind of laptop models like Dell 5520 and DV6, and there are some list of many more notebook motherboard using this specific embedded controller. And I'll also give you the list of the laptops where the common laptops where this IO controller is used, and in that case we need to program it. And how do we program it? After going through this data sheet, it would be very much crystal clear how to program this IO controller. So let's go into the details. This embedded controller contains the industrial standard 8051 microprocessor and provides function for 8042 keyboard controller. Any IO controller used in notebook motherboard, any IO controller used in recent kind of notebook motherboard will have two things, two internal controller. One is 8051, right, and another is 8042. 8051 is microprocessor and 8042 is keyboard controller. So we'll discuss this part also, 8051 and 8042. Many people, I think this many people are a little bit confused about a microcontroller and microprocessor. Well, this is out of topic, but I'll just briefly mention. See, a microcontroller is having microprocessor, RAM, clock, everything inside it, whereas a microprocessor don't have RAM or clock inside it, right? So a microcontroller is a whole unit. You can find it in any kind of devices, all kind of devices, like a mixer grinder used in kitchen, they also use the microcontroller, or the glue binding machine, they also have a microcontroller, or in automobile or car they also have microcontroller. But microprocessor is CPU, that is Intel dual core i3 i5. So a basic difference between a microcontroller and a microprocessor is that a microcontroller has processor, RAM and clock inside it. So this KB9012 is a microcontroller. Inside it you'll find a processor, that is 8051 processor, and a 8042 keyboard controller. So let's go again. The embedded controller also features PS2 interface, keyboard matrix encoder, PWM encoder controller, A to B converter, D to A converter, fan controller, SM bus controller, SPI controller, and extended interface. Well, you might think that why we are going into so much theory, but if you want to ask questions like why and how do we understand things, we must understand these data sheets, and that's why I'm going so deep. I'm trying to explain each of the things, and after we finish this class, we'll be using all those concepts to diagnose. Our ultimate purpose is to repair within minimum time and with minimum cost. But to do this, we need to understand all these things, right? So let's go ahead and let's go to the next page of this data set. Yes, so this KB9012 has features of LPC, that is low pin count interface. What exactly is LPC? Let's see in the data in the schematic diagram of DB2000. LPC, as discussed in the very first class, this is a bus technology, a communication bus technology between ICH and IO controller. Similarly, we can see over here, this is a communication technology between PCH and IO controller. Any data transmission between these two chips has to be done through LPC, that is low pin count. Any data transmission between PCH and IO controller has to be through LPC, that is low pin count interface. So this is LPC. And well, the question is, what is this then? Where is this bus located? Of course, there would be some physical pins on IO and there would be some physical pins on PCH. The question is, why we have so many different types of bus technology? Why can't we have a single bus? Well, that depends on how fast these interact. See, to understand buses, I'll just give you a very simple analogy. Is that, suppose I'm from India and my friend is from Germany and he wants to interact with me, but I don't know German, he don't know my Indian language Hindi, but we still want to communicate between us. So how do we communicate? We'll communicate in a common language, that is English, right? English is a kind of common language. We both can speak easily, right? So we can communicate easily between one common language called English. But to understand English, we must know I must know English well, and my friend from Germany, he also should know English well, right? That is, some part of my brain can decipher English, right? And some part of his brain can decipher English, right? Similarly, we have to communicate between two different kind of chip. One is PCH, which is entirely different. This is made by Intel, and this IO controller, this is here in this case, it is made by ITE, a different company, right? From a different, you can call it as a different country, whereas PCH is made by Intel, and these two chips has to interact, has to communicate, has to pass data. So how would they pass data? Until and unless they implement a common interface, a common language, a common interface. And between PCH to EC, LPC, low pin count bus, is a common interface. So both of this chip should implement LPC in their chip, right? So we'll find a LPC section in PCH, we'll find a LPC section in EC. Similarly, we have FDI, you see here in the circuit, you see, let's zoom it out. Here you see FDI, DMI. So between processor to PCS, there should be a common interface, and we have FDI and DMI. So an FDI implementation should be in PCH, a FDI implementation should be in processor. Similarly, a DMI implementation should be here and a DMI implementation should be in processor. Similarly, of PCI Express. So to understand the bus technology, you should always remember my analogy of communicating between two people of a different country, right? We must, so these two chips are also different, right? These two chips are also different, but they can pass data, right? Every data has to be passed from processor to PCH, from PCH to IO, and they're all passing data through different buses, but they have a implementation of those buses inside the chip. So any different company who would like to make a different kind of PCH, they must implement an LPC interface, right, to communicate with any kind of IO controller. Any kind of IO controller would have this LPC interface, right? I have also given you this presentation before the class to go through this LPC details. I am not referring this PPT in detail. Just I will be using some part of it because I think you have already gone through this PPT, right? So let's see what is exactly an LPC. If you want to go into more details about LPC, you can refer this presentation which will already be emailed to you, because I don't think that we could be covering the entire LPC interface in this class. So just important things will be referring. Okay, so let's see where is the LPC, right? LPC interface. Yes, this is LPC basic concepts, right? So here it's written LPC is a connection between Southbridge and Super IO, right? And this is host ISR and PCI host and LPC. So it's a kind of bus technology, and we can also refer the details of these pins. So when we go ahead, we'll come back again to this slide to understand the meaning of each of these pin details, right? So let's go again to our data sheet, right? SIRQ, this LPC low pin interface SIRQ supporting IRQ1, IRQ12, SCI, SMI. What is this SIRQ? SIRQ is serial IRQ. This is a kind of interrupt which IO controller generates, and these are the two common kinds of interrupt, IRQ1 and IRQ12. This you can find it in any IO controller, and IRQ1 is for keyboard and IRQ12 is for touchpad. That is, when we press a key on a keyboard, how does my processor understand that a key has been pressed? And when I press my hand on touchpad, how does that processor understand that a touchpad has been pressed? There must be a mechanism to transmit these data, because CPU, you know, these are all man-made. They don't have intelligence. They can't see anything. So there must be a intelligence involved which differentiate between my pressing a touchpad and my pressing a keyboard. There must be some kind of intelligence, and here is this intelligence. IRQ1 is generated through IO controller when a key is pressed, and IRQ12 is generated by IO controller when a touchpad is pressed. And we will understand all of these things in while going ahead, right? And IO address decoding 60H and 64H, 62H and 66H. These are a kind of address which are kind of fixed address, and we'll see how important these addresses are. Memory decoding, that is firmware hub and LPC memory hub. We'll also differentiate between the different kind of BIOS chip that is present. One is the LPC bus, that is SPI BIOS chip, and another is hub, the firmware hub chip. So we'll go into those details, right, later on in this class only. And this is X bus interface. That is well, there is a difference between an X bus and difference between X bus and SPI. X bus is a technology that was previously used, and nowadays it's used SPI, that is serial peripheral interface, right? Serial peripheral interface. So we'll discuss more about this. Okay, 8051 is the internal microprocessor. Any IO controller will have this 8051 microprocessor. If you talk about going into details about 8051, it will require around 20 classes to describe about 8051, right? So I'll not go into this detail, just use some basic concepts of how does they process data. Not go into details of 8051 microprocessor, because if you want to really understand this 8051 microprocessor, you have to take my another 20 classes to understand this 8051 microprocessor. Everything can be answered, everything can be explained. Nothing is hidden in electronics. You can answer everything, why, how, where, because it's all man-made. Anything in the world which is made by man can be answered, can be explained, but not nature. You cannot explain something which are made by nature, and that's why that is mystery. right? Because what I do is I always ask questions why it is possible, and at one point of time I don't find any answer. And why I don't find any answer is God's magic. You cannot explain each and everything that is happening in nature. There is some superpower, but we are close to that. The man is close to that because we have invented a intelligent system like microprocessor, microcontroller. We have devised such things. So if you work on that level, like explaining like how these two chips can communicate, when we have devised a common communication interface, right? So these are all internal details, but we must understand those internal details a little bit if we are into electronics fields. That's why I'm referring those things, right? Because it's not at all related to repairing. I must answer you, it's not at all related to repairing. You can also repair. There are 4 major IC present on a notebook motherboard. You can try replacing those 4 major IC. You can try replacing. You can try reflashing. You can try changing the power controller, and you can repair at least 60 to 70% of ports. But it will take you time, and it will take you cost. So we are going into such details, and we're using these concepts also. I'm reiterating it again and again in order to generate interest. You must understand these things. You must understand these things. If you want to be in this profession, if you want to earn from this profession, you have to understand these things. You cannot just fly away. You cannot run away from this concept that is too tedious. I cannot do this. No. If you can say like this, you should not be in this field, because we have to understand these things, right? And the boards are getting more complex and complex. But if we just, what important things that I'm telling you, why I'm reiterating is that some of my students have told that, sir, I cannot understand some portion of your talk. And I told him, you repeat my classes 5 times, you'll get through my class. And he emailed me that yes, he saw my video 6 times and he got it in the 7th time. And I say, good, okay. So let's go ahead. This is a 8042 keyboard controller. Well, we'll discuss this part, this 8042 keyboard controller and internal keyboard matrix and PS2 controller, how these are related. How these are related from a desktop keyboard, how a desktop keyboard is different from a laptop keyboard, right? We'll try to answer these questions, right? We'll try to answer all of these questions. This is, so internal keyboard matrix, this is present in all kind of IO controller. Embedded EC is there, and SM bus host, SM bus must be there. This is SM bus is also a communication interface to communicate data on 2 wire, right? To communicate a data between battery and IO, between IO and CPU. This is all SM bus technology, right? SM bus technology. We have already referred this SM bus in our previous classes also. And DAC, that is digital to analog converter, and ADC, that is analog to digital converter, and PWM we have covered it in great details in our 3.3 5-volt regulator class, and watchdog timer will discuss all about this. Real-time clock, GPT, general purpose wake up, general purpose input output, fan controller, CIR. How does this CIR, consumer infrared, how does it works? We'll see all these things, right? ESB, EDI, this is very important. ENE debug interface. Why this is important is because this 9012 IO controller requires programming if you solder a new IO controller, and you can program it only when you understand this debug interface. All right, SPI device interface, 1 wire, and PECI. PECI is platform environment control interface. We'll see about this also. This is a very important concept. PECI, platform environment control interface. All right, let's go ahead and the various things. So let's first discuss the first portion. Let's go to see the block diagram. And to understand anything is we must first simplify that thing, and the simplification can be done in the block diagram. Let's go to our schematic first, because the purpose is to understand the schematic. This is page number 40, and I would be dividing this class in, I think, 3 classes, and today I will be just discussing this part, this keyboard matrix. We'll discuss about this power, the various power, the V standby power, VWAT and AVCC also. We'll discuss all things. But let's first discuss with a very interesting question. The question is, the laptop keyboard is, what kind of keyboard it is? Is it a PS2 keyboard or is it a USB keyboard? Of course, everybody will say that it is a PS2 keyboard. And of course, this is PS2 keyboard. But what is a difference between a keyboard, laptop keyboard and a desktop keyboard? Have we ever seen any differences between a desktop keyboard and a laptop keyboard? And yes, there is a lot of differences between them. And the difference is that a desktop keyboard there are basically 2 kind of ICs present. One is keyboard controller and another is keyboard encoder. That keyboard encoder is present inside the desktop keyboard and keyboard controller is present inside the IO controller. And what is the keyboard controller? And we have already seen 8042. 8042 keyboard controller is present inside this chip, and the keyboard encoder is present inside the desktop keyboard. Whereas in laptop keyboard, both this keyboard encoder and keyboard controller are present inside this chip. You can see this data sheet as we've already discussed here, and I've started with the interesting things to understand this IO controller, because this is a really very awesome thing. Yes, and we've already seen this has, yes, you can see internal keyboard matrix. What does this mean? Basically there are 2 kind of controller. One is 8042 keyboard controller and another is keyboard encoder. In a desktop keyboard you have that keyboard encoder present inside the keyboard, right? Whereas the keyboard controller is inside the IO controller. But in a laptop keyboard, if you dismantle that laptop keyboard, if you try to dismantle a laptop keyboard, you won't find any IC present in that laptop keyboard. This is because both keyboard encoder and keyboard controller are present inside the IO controller, whereas in a desktop keyboard, the keyboard encoder is present inside the desktop keyboard and keyboard controller is there. So let's understand how this, when we press A, how this A is transmitted to CPU and how that CPU processes and it writes A. Let's understand that process first. See, there are 2 kind of controller as we already discussed. One is the keyboard encoder and keyboard controller. Keyboard encoder, let's consider the case of first a desktop keyboard. A keyboard encoder is present inside a desktop keyboard, and a keyboard controller is present on the laptop motherboard in IO, right? So what happens is, inside desktop keyboard you'll find various horizontal and vertical circuits, right? So when we press A, let's consider when we press A, so what happens is it connects that circuit, it transfers current. A current can be moved through that because the circuit gets closed, so a current can move, and that current goes to the 8048. The 8048 is internal keyboard encoder, right? There are 2 kinds, 8048, 8042. 8048 is inside desktop keyboard and 8042 is on motherboard, right, inside IO controller. So what happens is, When we press A, both those wires get touched, circuit is completed, current flows and goes to the 8048 keyboard encoder. Kindly note, I am saying keyboard encoder. Keyboard encoder is inside desktop keyboard and keyboard controller is onto the laptop motherboard. So the current flows, right? So the current flows to the keyboard encoder, and this keyboard encoder, since this keyboard encoder is also a microcontroller, it will generate two codes. We call it scan in and a scan out. You can see the schematic over here. KSO, KSI. What does this mean? Keyboard scan out, keyboard scan in, right? Keyboard scan out, keyboard scan in. But in case of desktop keyboard, you have two interfaces. One is PS2, another is USB. So not this, for each key you get a scan in and scan out. There are two codes generated for when you press any key, two codes are generated. One is scan in and a scan out, and that data is transmitted by the keyboard encoder via PS2 or via USB to the keyboard controller, right? To the keyboard controller. And there are two fixed addresses. One is 60H and another is 64H, right? 60H and 64H. So these are the two fixed addresses, 60H and 64H. I'll give you a scan of my copy in which I have discussed these things, right? So basically as I have told, there are two kind of controller. One is the keyboard controller and another is keyboard encoder. So in desktop keyboard, the data for when we press any key, two kinds of code are generated, that is scan in and a scan out, and that data is transferred via PS2 or USB to the keyboard controller. But this microcontroller have some internal registers, right? As we have already said, a microcontroller is different than a microprocessor. This microcontroller has internal registers. You can see in this data sheet. You can see in the block diagram. Let's see the block diagram first to understand this. Let's see. Okay, let's see this block diagram and let us understand this block diagram. This is block diagram of KB9012 IO controller, and like KB9012 IO controller, all IO controllers are internally divided into this kind of subsections. And as I said, inside this IO controller we have a microcontroller. And what is the difference between microcontroller and microprocessor? A microcontroller will have processor as well as RAM, clock, everything inside it. So let us find out RAM and clock. You see 8051, this is processor, and where is RAM? RAM is 4 KB static RAM is there, and we must have a clock. You see here is clock. So inside this IO controller we have LPC IF interface. LPC interface is for communicating between IO controller and ICH or PCH. So this is the only way to transfer data from IO controller to ICH or PCH. We can see in the schematic diagram. Here is the LPC bus interface. This is KB3910, which is an IO controller in DB2000, and you see the inside IO we have LPC bus interface, and this is LPC bus interface. LAD 0, 1, 2, 3, this is for data addressing, right? And L frame, we'll also see what is the function of L frame, L clock and serial IRQ. These are very important pins. And similarly we can see in the Lenovo Y470, you can see LPC. This is LPC, right? You see here LPC, LAD 0123, LPC RST, L frame, LPC PD, and we'll see what are the working of each of these pins and each of the signals. So let's go back to our data sheet, and we have EDI. EDI is embedded debug interface, and this is a important function or module built in this IO controller 9012, where you cannot find such module built in every IO controller, but in this IO controller there is a module embedded debug interface. That is, you can debug this IO controller through external ways, right? And we'll see this is a very important features. And why this is an important features? Because inside this IO controller we have an embedded flash, so we need certain ways to access that embedded flash, and this is one of the ways. And we have XBI, that is X bus interface, and GPIO. GPIO means general purpose input output pins. Out of 128, 106 pins are GPIO. That is, we can configure each of these pins either as input or output according to our task. So the manufacturer of laptop motherboards can use this IO controller to basically configure any of the pins as input according to their task or according to their schematics. So let's see with DV2000, you can see this GPIO. You can see these are all GPIO. Some of the GPIOs are not used, so a cross is there, and some of them are testing point. You see TP102, TP104. Some of them are configured as input and some of them are configured as output. Maybe you may find some cases where this same IO controller is used in different motherboard, but pin number 118 you see is configured as output. Maybe that 118 number pin may be configured as input. It may be case. It is 100% possible because these are GPIO, general purpose input output pins. This can be configured, right? This can be configured. And you can also see in this case, here you'll find GPIO pins. These are all GPIO pins with several functions like ODD_EN, NumLAD, user_button, and we'll see each of these functions. Okay. So let's go back over here. Similarly, there is a PWM section, fan section, and we have SM bus, watchdog timer. This is also very important. You can see here. You can see here the fan, GPIO is there, PS2 interface is there, SM bus is there, PWM is there, wake up is there. Then SPI enable interface is there, analog to digital, digital to analog interface is there, and here also in DV2000 also we can find this in those interfaces, PS2 interfaces, analog to digital, digital to analog. So you can find that all IO controller are basically having same subsections inside it, right? Same subsections inside it. And why is like this? Because our ultimate task is to process data and send data to ICH, or to control battery charging, or to control ACPI. So the basic of each IO controller is same, but there is some modifications done. Okay, so now we'll go down and we'll see here. This is having 128 pin 9012. This is very important, as I'm saying, because you can commonly find this IO controller in many kind of newer boards. 128 pins. Okay, let's go down and see what are the important features in this data sheet, and we'll correlate with our two schematics. And if you can be able to correlate these two schematics, you can really correlate any kind of schematic, right? Any kind of schematic you can correlate, and repairing by a schematic is the correct way. You might get experience after spending 10 to 12 years in repairing, but you can get those experience when you understand these schematics. Okay, so let's go down and we'll see the pin descriptions. We want to know the functions of each of the pins. Hardware trap, yeah, and this hardware trap pins is of very important for this IO controller, particularly this IO controller. You can see the pin number 39, TP underscore test, TP underscore PLL, TP underscore TMUX, TP underscore PLL underscore lock. And this pin is 39, but it can be configured as KSO0, KSO1, KSO2, KSO3, or as GPIO pins according to the laptop motherboard. Here we are talking of this IO controller. We are not talking that this IO controller is used in this laptop motherboard. We are talking of universal. So a data sheet will mention universal things. That's why they have written that this pin number 39 may be used as GPIO pin, GPIO 20 in some motherboard, or maybe used as keyboard scan out 0, or maybe this pin may be used as keyboard scan out 1 or as GPIO 21. But if this pin is what is the importance of this pin? The importance of this pin is to test the internal DPLL clock circuit, and if this trap is asserted to be low, the internal DPLL circuit will use another clock source. Why another clock source? Because we want to everything, every goods that is manufactured needs to be tested, right? It needs to be tested. A company, a factory can manufacture thousands of pieces of IO controller, but there must be certain ways to test those IO controller. And how can we test this IO controller? Not by fixing in that motherboard, but there must be some internal, there must be some external ways of testing this IO controller. So in case we are testing this IO controller, we need clock, we need supply, right? Then only it can work. So in that case, we'll apply a different kind of frequency, that is test clock mode. So if we ground this pin, the internal microcontroller will know that it is in test mode, right? It is in test mode. It is not in working mode. Not in working mode means it is not fixed to the motherboard. It is tested externally, right? So if this pin is asserted to be low, then the internal DPLL circuit inside IO controller knows that it has to use another clock source except this 32 kilohertz oscillator. Okay, and for us these two pins are very important, the pin number 41 and 42. And why it is important is because this IO controller has an embedded flash. So we need certain ways to access that embedded flash, right? We need certain ways to access this embedded flash. So this company has provided some way to access this embedded flash, right? And the concept is called flash direct access, right? If we put these two pins to ground, then this IO controller would be we can access the concept clause flash direct access. And what is flash direct access? That is, users can flash and program a SPI flash via specific IKB pins with external tools. That is, we can also flash the SPI flash, which is connected with the IO controller without removing this SPI flash and fixing it to the socket of BIOS programmer. We can directly program it via the keyboard connector present onto the laptop motherboards, right? And how is it possible? You can see it's written flash direct access. The KBC provides a new interface to program SPI flash via IKB interface, that's the internal keyboard interface. With this feature, users can easily utilize 4 pins from keyboard matrix without deassembling whole machine. And these 4 pins are connected directly to external SPI flash interface. And you can see over here what are the 4 important pins: SPI CS, SPI clock, MOSI, MISO. We can see in the data sheet. You can see in this data sheet for the SPI flash. These are the 4 pins which are important, right? SCK, SCE, serial out, serial input, and serial output. And you can see in this data sheet, these 4 pins are connected from IO controller. And if these are the 4 pins of the other part of IO controller, that is the keyboard controller. You can see here, over here you can see they have written KSI4. So let's see here, KSI4. Where is KSI4? Yes, this is KSI4, right? KSI4. And we can also see KSI4, KSI5, KSI6, KSI7. So you can see KSI, KSI4, KSI5, KSI6, KSI7. By utilizing these 4 pins, we can program this one only in 9012. Only in 9012. That is, these 4 pins is if we transfer data through these 4 pins, then data would go outside these 4 pins to the SPI flash chip. We need not have to remove that flash chip and put into socket. We can program that flash while keeping it on notebook motherboard, and this is a very innovative concept, that is flash direct access. We can directly access that flash via this IO controller. That is, if we can access these 4 pins by these 4 pins, KSI4, KSI5, KSI6, KSI17, and to enable this functionality, what we have to do, we have to ground this 41 and 42 to low. You can see low is test mode. That means considering this is KB9012, we have to ground pin number 41 and 42 of this IO controller. 41 and 42. If we ground these 2 pins, 41 and 42, then we can, if we transfer data through these 4 pins, the data will go out from this IO controller to the flash without removing flash. So we can use this concept, you can use this important feature of KB9012 to flash the external SPI flash as well as the internal SPI flash, and we'll see how we can do it. So in the end, you can see we already know these all pins are getting connected to the keyboard connectors, right? All are getting connected to the keyboard connectors. Some of the engineers across the world, particularly in country like Russia, have basically discovered a kind of device to program this embedded flash. And what they have done basically is have used this mechanism to design this. So we actually do not need any kind of devices to program this embedded flash if we know the concept inside it. We can use our TL866CS or A, better if you have A, because A is is a serial programmer, right? So you know, in a serial programmer, the TL866A is having a port, and you connect that cable to the laptop motherboard. You supply power over here. You supply the power, that is AVCC, and you ground the pin number 41 and 42 to ground. This 41 and 42 to ground. Then that case, this IO controller it will indicate to IO controller that we want to access the flash direct access, and via these 4 pins we can transfer data through the BIOS programmer, through TL866A. You got my concept? I will show it in video also when I will be discussing the BIOS programming, how to basically flash this embedded flash inside this 9012 via TL866A. You don't require any new kind of BIOS programmers. Some people are selling stuff for programming this embedded flash, but in fact you do not require if you know this data sheet, if you understand this data sheet. Okay, so this is flash direct access, and this is only in 9012. That is, you can transfer data via these 4 pins to this SPI flash, and this is a very innovative, right? Very innovative. So let's go down and we'll discuss more about it later on in this data sheet, and I'll provide a video of how to program that embedded flash, because this is a very common problem encountered nowadays by technicians. So this is a pin description by functions. Let's see the low pin count interface, and let's go over here. In this data sheet we have LPC bus. Okay, so what are the important pin numbers? LAD 0 to 3. So there would be 4 pins for the LPC address bus. You can see LAD 0, 1, 2 and 3, and these 4 pins are connected to the PCH, right? These are the address bus line. That is, via these 4 pins the IO controller transfers the address, right? Transfers the data to the PCH. And L frame is the LPC frame control signals, and we can also see in our presentation. Let's go back to our presentation. This presentation I have already provided to all of you. To see more details about LPC, I have given it because I cannot discuss all these things in one class, so I have given it to you earlier, so that you go through this video, go through this presentation and understand a little bit about the LPC. Okay, and we'll also discuss this part. This is a very important part. What is TSOP, what is PLCC, what is SOP8, and how can we capture these signals through oscilloscope when we discuss the oscilloscope, how to test the oscilloscope. This is LAD03 in official data sheet, official description of LAD03. It is called multiplex command, address and data. That is, command, address and data, all these 3 things are transferred across these 4 lines, right? All this command, data and address are transferred across these 4 wires. All right, and we see L frame. L frame means it indicates the start of a new cycle and termination of a broken cycle. As I've already spoken, that we want to communicate between a PCH and IO controller. Both are made by different companies, so we must have some kind of interface in both of them to understand. So LPC bus interface is in IO controller also, and we can see in PCH also. Let's go back to the PCH pins to describe more about it. Let's go to page number 11. I think there would be an LPC bus interface, not here. NCTF is also very important for you might get a message on your laptop sometime that your BGA ball is cracked, right? BGA ball cracked, and you might require replacement of chip, BGA chip. How that message is generated through this NCTF, a very important in PCH. we will discuss more about in PCS. Let's find out the LPC bus interface of in PCS. Let's go back to the page number 12. Because I said these two chips are made by different company, so they must have a common interface to communicate data, right? To communicate data, they must have a common interface. Let's go to page number 13. 13. Wait. Now this is the last page, I think. So let's start with the first. PCH strap. Yeah, this is LPC. You can see over here, this pin is directly connected to the IO controller. So inside PCH there is a LPC interface, and inside IO controller there is a LPC interface. So you know, both have this interface. Similarly, if I'm talking to a Chinese person, how can I communicate with him? I can only communicate with him in one common language, that is called English. Both of us can understand that English language, right? So some part of my brain, that is, for that I must learn English and my Chinese friend must learn English, and we can communicate in a common language, English, right? We can communicate in a common language, English. So some part of our brain must have implementation of that language. Similarly, this LPC bus implementation is there in PCH, and this LPC bus interface implementation is in IO controller. So let's go back there. Let's go with, I think it's 31 page number, not 31. So many data sheets I can go across every day. So this is page number 40 in fact. So we were discussing this LPC bus interface, and we have also seen the functions of each of them. Let's go back over here. LCLK, this is clock. L reset, that is reset, right? That is reset. So, and let's go to see more about it. SERIRQ, this is serialized IRQ, only needed by peripherals that need interrupt support. Now this is also a very important concept. In fact, SEIRQ, this is a serial IRQ, is basically given to indicate whether, suppose a user presses keyboard and suppose the user presses touchpad, how would this IO controller know that user has pressed keyboard or user has pressed touchpad? How would that processor know? So this IO controller must indicate to processor that a touchpad has been pressed or a keyboard has been pressed, so that the processor can process this data accordingly, right? So there must be some way to transfer to the information to the CPU that yes, a touchpad has been pressed or a keyboard has been pressed, and for that a specific kind of interrupt has been made, and that is we call serial IRQ. And there are two types of, earlier there used to be two pins on the IO controller, one is IRQ2 and another is IRQ12. IRQ2 interrupt is generated by IO controller when you press keyboard, and IRQ12 interrupt is generated by IO controller when we touch touchpad. But nowadays this is combined in one, serial IRQ. So this serial IRQ interrupt is sent to processor to indicate that a keyboard has been pressed or a touchpad has been pressed. So this differentiate, right? This differentiate. So let's go back to our data sheet, right? Back. PS2 interface, PS/2 interface. So we can see in this data sheet. Let's see in the DV2000 we have, similarly in the DV2000 we have LPC bus interface. Here also you can find serial IRQ, LCLK, L frame, and this data and this LED 0123, that is command data address pin, right? And so let's go back over here, that is PS2 interface. The question is whether our keyboard, laptop keyboard, is a PS2 interface or a USB interface. So let's see more details about this PS2 interface. Actually, the question that we're asking is whether a laptop keyboard is a PS2 or a USB. In fact, a laptop keyboard is a PS2 keyboard. Very obvious question is that it is a PS2. You can call it is a PS2 keyboard. But there are certain differences between a desktop keyboard and a laptop keyboard, and we'll see what are the important differences, because understanding the difference is also very important. So we'll find out where in the schematic we have a PS2 interface. You find out this is a PS2 touchpad clock and touchpad data, right? Touchpad clock and touchpad data, and this is sent to pin page number 35. Let's see, where is this page number 35? Yes, this is page number 35. TP clock and TP data, right? TP clock and TP data. Yes, you see, this is TP clock and TP data, and then we have the touchpad circuit, right? Touchpad circuit is there. This is connected to the touchpad circuit, right? So we see over here in the schematic, this is the PS2 interface. So this KB9012, this KB9012 has in fact 3 PS2 interface, right? And we can use any one of these 3 PS2 interface, or we can use all 3 of them, right? All 3 of them. And now we see internal keyboard encoder. So where in the schematic is internal keyboard encoder? This is internal keyboard encoder. All these pins are internal keyboard encoders, also called keyboard matrix. There is quite a difference between internal keyboard encoder and keyboard matrix, and we are going to discuss that thing. In DB2000 also, let's see, this is the keyboard matrix, and we'll also see the PS2 interface. Again, PS2, so the touchpad is a PS2 interface, right? And in an IO controller we have a specific pins for keyboard, whereas in desktop keyboard you won't find this specific pins for keyboard, right? Only there are PS2 interface, PS2 keyboard, PS2 mouse, or USB keyboard, USB mouse, but no specific pins for keyboard in desktop keyboard, and this is a difference. Now I'll explain you what is exactly inside a keyboard. Let's talk about a desktop keyboard. In a desktop keyboard, if you dismantle a desktop keyboard, you'll find a circuit inside a desktop keyboard, whereas if you dismantle a laptop keyboard, you won't find any circuit inside it, right? So this is one difference. Actually, there are two kind of keyboard controllers. One is onboard keyboard controller, that is present onto the laptop, onto the motherboard, and one is keyboard encoder. Right now I am talking about desktop keyboard. So in desktop keyboard we have two kind of keyboard controller. One is onboard keyboard controller present onto the laptop, present onto the motherboard, and another is keyboard encoder that is present inside the desktop keyboard. So when we press a key, on a desktop keyboard, what happens? It basically closes a circuit and a current flows, and that current goes to the keyboard encoder. It is a kind of microcontroller, and usually this microcontroller is 8048 microcontroller present inside the desktop keyboard. And we call that microcontroller as keyboard encoder, right? Please note, I am talking about desktop keyboard right now. So in desktop keyboard we have two kind of controller. One is keyboard encoder, keyboard controller. Keyboard encoder is present inside the desktop keyboard, and the keyboard controller is present onto the motherboard, right? And what are those two types of controller? 8048 is keyboard encoder present inside the desktop keyboard, and 8042 is a keyboard controller present inside this embedded controller, right? So when we press a key on a desktop keyboard, what happens? It closes this circuit, it gets grounded, so the circuit is completed. A current goes to the 8048 keyboard encoder, and for each key it will generate two code, scan in and a scan out, and those two signals, those two data are transmitted by the keyboard encoder via PS2 interface to the IO controller, right? Because an IO controller has PS2 interface, right? It has a PS2 interface. A desktop keyboard will have no such pins. So a desktop keyboard is connected to the IO controller via this PS2 interface. So those two data, scanning and scan out, is transferred to the IO controller from the keyboard encoder to 8042. There is a 8042 keyboard controller inside this IO controller. Those two data, scan in and scan out, are transferred to that keyboard controller, and that keyboard controller reads those two scan in and scan out, send this data to CPU, right? But before sending this data to CPU, what it will do? As I say, serial IRQ, right? SERIRQ. What it will do is, it will first send a signal IRQ2. 2 means keyboard. So it will send a signal to processor, and that will let the processor know that yes, a keyboard command is there. Keyboard command, those data would be sent through these 4 pins to the processor. Processor will read it, and the operating system would convert those two signals via ASCII character, and it will press that key. That key would be displayed onto the screen. You got my point? What are the process? As I said, there are two kind of controller. One is inside desktop keyboard, one is inside the IO controller. The keyboard encoder present inside the desktop keyboard is 8048. The keyboard controller present inside the IO controller is 8042. When you press a key, current flows. The keyboard encoder will generate two data, scan in and scan out. Those scan in and scan out are sent to the 8042 keyboard controller present inside. It will process that data, send to the processor by enabling serial IRQ. IRQ2 is for keyboard, IRQ12 is for touchpad. Here the data is coming from the keyboard, so IRQ2 will be sent, and the data will be sent via these 4 pins to the processor. Processor will process those two scan in and scan out, and will generate the character. This is the actual process, and a lot of stuff is involved. And there are two fixed addresses, 60H and 64H. 60H and 64H. These are the two data, and I'll also send you the scan copy of the notes that I made for this keyboard concept, because one of my student has asked this question from me, sir, that he's a little bit confused. What is actually difference between a desktop keyboard and laptop keyboard? Right now I have talked about desktop keyboard, whereas now let us consider the case of laptop keyboard. In laptop keyboard, when you dismantle a laptop keyboard, you won't find any controller inside this laptop keyboard. So how they are operating, and why a controller has not made inside this this laptop keyboard? We have not included the controller inside the laptop keyboard to make it more robust, to save space, because laptop is for saving space, right? What we have done is we have connected the pins, these direct pins inside. That is, this IO controller has two parts. The keyboard controller and keyboard encoder is both inside this IO controller, as you can see in this data sheet. You see over here, this is internal keyboard encoder. That is, the encoder is present inside this IO controller, whereas in a desktop keyboard this portion is not there. And this is a difference. That is, this IO controller in a notebook keyboard has two parts: internal keyboard encoder and keyboard controller, and the pins are directly connected over here. The data would first get processed by the keyboard encoder and it would get internally transferred to the keyboard controller, right? Whereas in desktop keyboard, we have the keyboard encoder is inside the desktop keyboard. Data is processed inside the keyboard and then sent to the IO controller through PS2 interface or USB interface, right? But here in this case, the data is all processed inside here, right? We press the pin and a scan in and a scan out are sent. These are processed by the internal keyboard encoder, sent to the internal keyboard controller, and then sent to the processor via these four pins. But how this data transfer taking place? There are two fixed specific port. One is 60H, another is 64H, right? 60H and 64H. That is, our CPU can communicate with the keyboard controller present inside a desktop keyboard. We can communicate directly, the processor can directly communicate with the controller present inside the desktop keyboard by the address 60H. That is, if we want to read the information from the 8048 microcontroller present inside the desktop keyboard, the CPU